not very loud. So better? Yeah. Most of this is not original work I'm talking about. It's a little more of a review of the field. A couple of projects I worked on with Duncan Forbes and Joel Pfeffer, which I'll discuss at certain points. So just to give an overview of some what I think are the important facts to know about globular clusters from observations in the low redshift universe. This is a diagram of M31 with its globular cluster system. And this is a metallicity bar here. So there's bulge, inner halo, outer halo populations. These are two different bulge populations. And you can see a metallicity gradient as you go out. So some of the key things to know about globular clusters is that they have old ages, but a wide range of both intrinsically spread of ages, but also very difficult to pin down the ages. It's better than, say, 1 gigayear, which makes a big difference in formation results. A wide range of metallicities, generally considered low metallicities. They're found in all types of galaxies, from giants to dwarfs. There's different populations, so it's sort of like it looks like we need multiple modes or formation sites for globular clusters, halo populations, bulge and thick disk populations in particular. Typical masses of, say, 10,000 to 1 million solar masses, sizes of a few parsec, and they represent a pretty small fraction of the total galaxy mass today. There's sort of a characteristic UV luminosity formation, just to put a reference of starting to reach those luminosities with JWST. Overall, the point is that these are old, and they seem to be a different mode of star formation than we get in the present day, so they should be providing us fundamental clues about what's happening at high redshift, which we can now start observing directly. So what do we know about the conditions for massive star cluster formation? There are some massive star clusters forming in the local universe, not very commonly, but there are some. And there's been a lot of observational work nearby galaxies to try to determine what causes different star cluster masses and mass functions to form. This is one example of a truncation mass or maximum mass of a cluster, and it's given its host galaxy a global star formation rate density. So there's this strong correlation. There's some argument about exactly what this means, but basically you only see the most massive clusters in the highest density star formation regions. And you also get the highest fraction of stars in clusters. So if you have high star formation density, you get lots of clusters, and you get high mass clusters. So an example you can see on the right is, where do you get that? Well, major mergers is the main site in the local universe where you get a lot of gas at high pressures. And I say that what we think maybe the physics is driving all this is turbulent pressure, which is allowing the formation of these high mass clusters. And that's major gas-rich mergers are a major place that happens in the local universe. But in the high redshift universe, those conditions can happen just on the main sequence of star formation. So it's kind of natural to expect that you get globular clusters forming in the high redshift universe. One little side note is I'll talk a little bit later about diffuse dwarfs, ultra-diffuse galaxies, some of them with a lot of globular clusters. So in this context, it doesn't make sense that a very diffuse galaxy would form a lot of massive clusters. So it tells us right off the bat that those dwarf galaxies must have been much higher density, let's say more compact than earlier times, just based on basic physics. Okay, so the next formation clue about globular clusters is their metallicities, and we can start using that as a tag to say, well, okay, without even thinking about models, let's just look at the observations about where these low metallicity environments when the globular clusters formed, where and when did those occur? And now with JWST, we're getting more and more data about the high redshift universe, the evolving mass metallicity relation. And so I'll put on here where the metal-rich clusters would be, say, in this range. So we're looking at potentially some relatively high mass galaxies at redshifts of a few. Okay, is where the natural place to form those. This is like the cosmic noon star formation. And the metal-poor ones, those would be lower mass galaxies at sort of redshifts of, say, 7, just kind of a guess. So this is all early days of figuring this stuff out. But already you can start to see there's constraints, is that if you're going to get a million solar mass cluster, or even higher sometimes, You're really going to form that in a, it's into the fifth, it's into the sixth mass galaxy. So you start getting some logical constraints on how you can form these things. Now that's, of course, stellar mass, and what we're really talking about is gas mass. So there's some mass budget considerations to start putting in here. And we already found a cluster that seems to break the constraints. There's one in M31, a million solar mass cluster with a metallicity of -3 that just doesn't seem to make sense in how you would form it in this context. So, of course, part of the picture is that there's a lot of scatter in these relations, and so you can always get unusual object, or you could conceivably get an unusual object by scatter. But this is the point, is that you can start putting these constraints in where the globular clusters are formed and when. So now starting to think about models for them, and generically all the models are forming globular clusters in high gas density regions, high pressure regions such as starbursts and mergers. And there's sort of, I'll break it down into there's maybe two general classes of models or simulations, say these days. There's ones that try to resolve the globular clusters, a parsec or subparsec resolution, and that still, the dynamic range is so problematic that this is limited to high redshift simulations only. So that's promising for starting to compare to the high redshift observations. Doesn't work for today's globular cluster comparisons. So the other sort of like maybe more common approach is to do some kind of subgrid model. You've got a standard cosmological hydrosim, and you add some ingredients for globular cluster formation with different prescriptions. And the one that I'll talk about a lot is really I think the most advanced in this context is called E-mosaics. In terms of, not advanced in terms of the actual underlying simulation, but the subgrid recipes for the globular clusters is the most extensive. And so what do those ingredients look like? Things like relating the cluster formation efficiency to the gas density pressure in the host galaxy, the cluster masses coming from things like the amount of feedback energy goes into the ISM, and again, the gas pressure folded in. So it's not just the formation, because a lot of globular clusters can disappear after they're born, and there's been some ideas that maybe 90% of them disappear. So you really have to model that as well. So processes like dynamical friction, two-body relaxation, tidal shocks, which also involves ideally modeling the ISM correctly to deliver some of those tidal shocks. So there's a lot of ingredients that go in to get this right. And I'll just show another observation that's sort of not folded into any of these models. This is another interesting part about globular clusters, is this whole area called multiple populations. It's an unsolved problem. So we like to think of globular clusters as like a simple stellar population, single age and metallicity, all formed in one burst. But when you look at them in detail, this is a color magnitude diagram with ultraviolet filters, and there's a split main sequence, which implies something like a helium variation. And the classic star-to-star variations in these light elements, nitrogen, aluminum, etc. And that's telling us there's some extra enrichment going on there, generally called first population and second population. And the big question is, where does that pollution come from the second population? Okay. So in general, this requires high temperature hydrogen burning to get those light elements, and there's various classes of stars that could do that. The problem is that people have been working on this for years, and there's all sorts of observational constraints. And the last I've heard, none of them seems to work. This is from a review by Bastian Lardo, where they sort of gave an overview of all the different polluters and all the different observational constraints, and basically lots of red X's where they don't satisfy the constraints. So it's been very hard to get these things to work. A lot of it's a mass budget problem of getting enough pollution going into the second generation of stars. So this is going to be a caveat that maybe this is kind of a just secondary worry, but maybe it's telling us something fundamental about globular cluster formation. So it's a possible caveat about all these models of globular cluster formation. They're not necessarily an extrapolation of globular star formation today. And can high redshift observations tell us anything about multiple populations? So I'll come back to that at the very end. So just to say, I'll maybe talk about conventional models, but just to say, until we have like a complete solution to globular cluster formation, there continue to be a long history of, we say, exotic, unconventional models of things like globular clusters forming in their own dark matter mini halos, stream collisions and falling streams. So a lot of people in this room have worked on some of these models. And We heard Avishai talk about feedback through starburst. So I won't get into those, but any of these can be compared to lots of observations that are out there, including now the high redshift universe. Okay, so now let's look a little more detail at one of the conventional models, the E-mosaics model. This is a Milky Way analog, or sort of a composite of a bunch of Milky Ways that were simulated. This is the overall star formation history of this Milky Way. This is what the globular clusters are doing in the simulation. Now, I've enhanced by a factor of 400 so you can see it. You can see they're peaking at early times, as you would expect. And we think that there's some enrichment going on at the same time, that this is where the metal poor globular clusters are forming, say, redshift of 4-ish, and metal-rich ones forming at cosmic noon around, say, redshift of 2, where there's a lot of activity going on in a massive galaxy progenitor. And so the question is, well, now that we can observe those redshifts, can we actually see those globular clusters in formation and see where they're forming in the galaxies? And keep it in mind that what's not really shown in this model is, you can see here how this metal poor peak is coming up above the overall star formation. I mean, it is amplified by a factor of 400, but there are some extrapolations. You see, if you just reverse the star formation history of the Milky Way and go to the oldest stars, if you go to old enough stars, half of the stars could have been in globular clusters at some higher redshift. So that's sort of what we could be looking for in these protogalaxies, these globular cluster-dominated galaxies. So let's start with this redshift of 2 cosmic noon. Of course, there's going to be a long time ago, these observations came in from HST and from ground-based adaptive optics of these turbulent disks, and which with these currently massive star-forming clumps that would be natural formation sites for forming globular clusters. You want to form a million solar mass globular cluster, what better place to do it than if you've got 10 to the 8 mass in the molecular clouds around? Okay, if you don't do it there, then where else are you going to do it? And so there's a lot of uncertainty about, like, how long do these live? I mean, are they really stellar mass clumps? So now JWST is results starting to come in. And find at least some of these galaxies seem to have long-lived stellar mass clumps. So that could start resolving some of these questions about, are these really places you could birth massive star clusters that survive? And say that we've done some work on kinematics of low redshift massive galaxies and these globular cluster systems, and we see this rotating systems that seem to be, could be the imprint of these early turbulent disk formations. Okay, so a problem with this, I mean, that looks like it might all hang together. One problem comes from the Milky Way is when you start looking in detail at what's called the mass-metallicity relation, and you compare that to standard models of globular cluster formation, which are these this blue area, that you get these really old metal-rich clusters that don't seem to match, and that comes with everybody's models that seems to have the same problem when you just compare to the Milky Way. So you're expecting these to say form a redshift of 2. But the observations of the ages seem to say there's a bit higher redshift. Now, and it could be even higher. The uncertainties are difficult to deal with. So it could be, okay, Milky Way is just an oddball. We kind of know that already. It's an earlier forming galaxy than usual, so maybe that's why. When you look at the E-mosaic simulations, you get 1 or 2 out of 25 that look roughly like this. Or it could be that, well, we have to keep looking at more galaxies and see if is the Milky Way really an oddball with the globular clusters, or maybe we're missing something with the models. And here's where we get JWST. Everybody was excited about the first release image, and we didn't realize it was really a lot of excitement about globular clusters. If you zoom in here, this is this really interesting sparkler galaxy, which I'll talk about. So this comes from pretty much everything I'll talk about from here on high redshift is lens systems, which allows you to see these faint compact objects. This is lensing behind this lower redshift cluster, and you got 3 images of this background galaxy. It's a redshift of 1.4. This is the one that you can really see the clusters in. So the stellar mass at that redshift is about 1 billion. So this is plausibly a Milky Way type progenitor galaxy. So we could be looking at a Milky Way in formation with a globular cluster system. There seems to be a lot of uncertainty in these magnifications, but so it's a little difficult to tell on the sizes. They definitely are compact. Exactly how compact we don't know. Exactly what masses we don't know. but they fit in with being globular cluster progenitors. They're a pretty large mass fraction here of the overall galaxy, which is also what we kind of expect to see if we go back in time. Whether you expect to see that high of a fraction is not clear to me. And what's nice about this is say, okay, well, this is only redshift 1.4. You know, that's not exciting. Globular clusters, you want to see them at higher redshift. Well, the point is that, you know, it's hard to tell the difference between redshift of 2 and SIN formation when you observe something today, but when you go back 9 gigayears ago, all of a sudden your stellar population models and your SEDs and your spectral lines can start telling the difference between those. So by observing something at half the age of the universe, all of a sudden you can start constraining when the globular clusters form. So if we can find more of these, you don't necessarily have to go to super high redshift to get some interesting constraints. If we can find more lower redshift things like this, it would be really useful. So Duncan Forbes and I just did a paper where we kind of tried to put together some different contextual constraints on this galaxy. Again, this age metallicity diagram. And in the Milky Way is these all these black points, and there's sort of this is the high metallicity bulge clusters, and this is sort of the young halo satellite track. And so the sparkler data points seem to fit in with those bulge clusters. I'd say this is from SED fitting from Maula, who studied this and reported this in detail. And so it looks at first glance like, so first of all, the formation redshift they got is between 7 and 11. So again, that's kind of unusually high in the standard models for metal-rich clusters. It should be more like 2. And then there are some like kind of younger ones, as you would expect. So it appears like, okay, maybe the Milky Way is not the only oddball. Here's already another one with these high redshift formation of globular clusters, metal-rich globular clusters. Now, the wrinkle is that another group came in and did a reanalysis of photometry, reanalysis of the SED fitting. They got a different result. They find that these points move down to be on the metal 4 track, so it becomes like as you would expect for a globular cluster system. So Lamita Maula has got some JWST spectra in hand now to try to resolve this through spectroscopy, IFU spectroscopy of this galaxy. So I'm hoping pretty soon we will have answers and we will resolve that question. What are really the ages, metallicities, and dynamics of this whole system? So, okay, the sparkler was just the first one you all heard about. All these different systems that continue to pop up with cute names, with lots of clumps seen in them. And so redshifts of 4 to 10, about globular cluster mass and sizes in a few parsec in general with a high lensing magnification. So again, these look like globular cluster progenitors. In some cases, up to 70% of the luminosity is in these clusters. So they look like cluster-dominated galaxy formation. Now that's the luminosity. That's not telling you the stellar mass, which is harder work to extract that. So some of the questions now, of course, we want to get more of the statistics and the demographics of these cases and which cases don't have these. Is this associated with burstiness, the massive star cluster formation? Are these, there's been some discussion, maybe some of these are mergers, or are they actually forming in situ? Some of the outstanding questions, I think. So in terms of theory, starting to look at this is what we'd like to see next is, now we've got some constraints at high redshift as well as low redshift. We can start seeing what models work or don't. This is Joel Pfeffer's work from a few years ago, sort of if you think of it, a prediction plot. So he's now looking at the new observations and seeing where those fit in. But a few years ago, this is what he's predicting: the brightness, sort of the UV fraction of the brightest cluster versus redshift, and this is color-coded by galaxy mass. And basically at high redshifts, you don't get, so most of them are down here, 10% or 20%, because you don't get a lot of light from these massive clusters on average. Although again, you could be seeing some extreme examples. So it's not clear that if the standard model is going to work with the observations, but it could be that there are enough of these kind of outlier galaxies that they do work, and that's hopefully Joel will have those results out before long. We can also start entertaining non-standard models and start thinking of, okay, what new physics are missing to explain these. And this is like work I saw from Sugimura et al., where they said, well, maybe, why would you get these massive clusters? These are some simulations they ran where they included this ultraviolet feedback, which they were finding that allowed you to delay the cooling of these clouds, forming these massive clouds and then massive clusters. So this, instead of 10 to the 4 mass clusters, you might get 10 to the 5 or above with this feedback. And so I think it's early days. I'd like to see more people work on how do you form these preferentially massive clusters at high fractions of the star formation. What do these high redshift systems look like? These are some standard mass evolution tracks from Peter Peruzzi. And so these are these stars are the actual observations of redshift and stellar mass. And so you just go to present day, you say, well, most of these are going to end up being these very high mass galaxies of present day, and high mass galaxies have lots of globular clusters. I'll just point out that this other system I mentioned earlier, we're finding these dwarf galaxies of low redshift with tons of globular clusters. And one possible scenario of those is that they're failed galaxies, which means they formed early and for some reason quenched and just carried on to the present day. So if you form something out here, lots of globular clusters and few stars, and then just quenched it, it might end up looking like that. So as a fossil of this globular cluster dominated epoch. And this one, about 13% of the present day mass is in the clusters. Very extreme. So Joel led a paper we did earlier this year trying to look at dwarf galaxy globular cluster variations in the Eagle E-mosaic simulation. Now, it doesn't have the resolution to do a lot of things we'd like to do with dwarf galaxies, but sort of this indirect line of reasoning that, first of all, the number of globular clusters at specific frequency correlates very strongly with the gas pressure. Part of this is just what you get from the model automatically. And then the gas itself is more rotation dominated when you have a lower pressure. So another way to say it is that when you get more globular clusters, you should have a dispersion supported dwarf galaxy. Seems to be a fundamental prediction. So we don't have enough kinematic data directly to address this, but we can look at flattening as sort of a proxy for kinematics. You know, if you have a disk rotation dominated galaxy, you've got a flat one, and looking at different correlations with number of globular clusters and the shape, the axis ratio of the galaxy. This is just one of 4 data sets we looked at, and they all show the same thing, that the more globular clusters you have, you might be able to kind of see it here, the rounder the galaxy is, which is these red histograms. And so this is a consistency check on this standard model that these earlier, more turbulent dwarf galaxies are the places where you also form the more globular clusters, and later on you get more settled disks and you get fewer globular clusters. So this kind of raises the question, as I showed these observations of massive galaxies at high redshift with lots of clumps. Well, we want to see some of these dwarfs in the observations with clumps. We see them at low redshift. We know they must have formed somewhere, so it'd be good if we can find some observed systems like that. So the one last thing is, I mentioned the multiple population mystery at the beginning, and we've all seen this plot multiple times now, of the famous GNZ11 with a nitrogen enrichment. What turns out is there's a bunch of them like that now, where this is a nitrogen oxygen abundance diagram of these are the star-forming galaxies in the local universe, and this is where these high redshift things sit. And that's where the globular clusters sit as well, okay, in that same region. So is this just coincidence? Are they literally globular clusters forming in those regions, or are those regions kind of emblematic of the star-forming conditions of these high redshifts that the globular clusters share in? They're compact regions. Again, we saw this plot or kind of earlier that those enhanced regions are also the compact regions as well, also be natural sites for forming massive star clusters. And again, it's early days for knowing what this means for multiple populations. There's some ideas that this could be very massive stars in these regions, the winds from the stars which are doing the second population enrichment. So there's just a summary of the conclusions, is that we know globular clusters formed at high redshift. We just don't know the details. Now we're actually starting to see some of the details at high redshift with these clump-dominated galaxies. If those are not the places that are forming the globular clusters, then where are they? The globular clusters are they hiding behind a bunch of dust somewhere that we're not seeing them? It's the most likely place they could be. The sparkler galaxy is a nice test of some of the models, and it may have some tension with the standard models. And again, this nitrogen enhancement is a very interesting parallel clue that might be telling us something about globular cluster mystery of multiple populations. So yeah, thanks for your attention.
Questions? Joe? Aaron. Thanks for a wonderful summary. You mentioned the Kalita paper, but what the Kalita papers have found, this is using JWST observations from Sears, is not just formation of globular cluster mass objects. Most of their objects are masses 10 to the 7.5 to 10 to the 9.5. In other words, an order of magnitude or more massive than globular clusters. So this confirms earlier results from HST that many galaxies, probably a majority of star-forming galaxies, have these giant clumps. What's the relationship, do you think, between these giant clumps and the globular cluster formation?
So what I'm not clear on, maybe you can answer this, is how well can we resolve the internal structure of clumps? Can we tell if there's some kind of fractal structure where there's multiple sub-clumps of stellar clusters? Or are they one monolithic clump? Do you know that?
HST's resolution is a kiloparsec at redshift 1 and above. But with JWST, the Kalita papers looked especially at redshifts 1 to 2, where the resolution is 3 times better. So many of these clumps were fairly well resolved. And they do, at least many of them, appear to be fairly monolithic structures. They also showed that many of these clumps are detected in the IR, in addition to the clumps that are detected in rest-frame UV, which also almost always have IR counterparts. So the point is that this massive clump formation is a separate phenomenon, I think, probably related to globular cluster formation, but it's not the same thing. These very massive ones would, of course, not survive in the galaxy. They would migrate fairly quickly to the bulge just by dynamical friction and maybe viscosity.
They could also lose mass if they do that. Yeah, well, I agree. It's not clear, but then again, we have to ask them where the globular cluster is forming if they're not in these clumps.
A quick one. Near, and the next speaker could approach to the desk, please.
Hi, Aaron. Thank you. Could you comment again? I was a little confused. Your result from the Sparkler galaxy, not only that you have old metal rich globulars, but that the metal poor globulars are younger than the metal rich globulars. I mean, how does that work in terms of galaxy assembly or like metal enrichment?
Yeah, I mean, you can get that. It's not so much that you have younger ones. That's fine. If the Milky Way has a lot of younger ones. These black points are Milky Way clusters, and they come from dwarf galaxies that are falling in and delivering younger clusters. What the puzzle is that we're missing these ones, the old metal poor ones, except for the reanalysis. So, you know, that reanalysis, if it's correct, would make more sense with the standard model.
Okay, thanks. Okay, let's thank Aaron again.